You wake up one morning and check your phone. The time says 8:15. You get dressed, make coffee, drive to work. Every clock you pass shows the same progression of minutes. 8:30, 8:45, 9 o'clock. Time moves forward at exactly 1 second per second. This feels so obvious that questioning it seems absurd. Time is universal. Time is absolute. Time flows at the same rate everywhere for everyone, except it doesn't. And we can prove it. Take 2 atomic clocks, the most precise timepieces humanity has ever built. These clocks are so accurate, they won't lose a single second in 300 million years. Put one clock on the ground floor of a building. Put the other clock on the top floor. Wait a few days. Come back and compare them. The clock on the top floor will be ahead, not by much, tiny fractions of a second, but ahead, measurably ahead, consistently ahead. The clock higher up experienced more time than the clock lower down. Same building, same week, different amounts of time. This isn't a malfunction. This isn't measurement error. This is reality. Time itself runs at different rates depending on where you are. Not what you're doing, not how you feel about it. Where you physically exist in space changes how fast time passes for you. Now take those same 2 clocks on an airplane. Fly one around the world, leave the other on the ground. When the plane lands, compare them again. The flying clock will be behind. It experienced less time than the grounded clock. Send particles racing through an accelerator at 99.9% the speed of light. These particles should decay, should cease to exist in millionths of a second, but they don't. They live longer, much longer. From their perspective, barely any time passes. From our perspective, watching them, they're living in slow motion. Your GPS wouldn't work without accounting for this. The satellites orbiting Earth are moving fast and experiencing weaker gravity than you on the surface. Both effects change how time flows for them. If we didn't correct for this, your GPS would be off by kilometers within hours. We adjust for time dilation every single day. This technology exists because time is not what we think it is. So what's actually happening here? Why does time behave this way? The answer starts with something that seems completely unrelated: light. Specifically, how fast light travels. In vacuum, light moves at approximately 300,000 kilometers per second. We call this speed c. And here's the strange part. No matter how fast you're moving, no matter which direction you're going, you always measure light moving at exactly c. Think about what that means. You're standing still. You measure a beam of light. It's moving at c. Now you start running toward that same beam of light as fast as you can. You measure it again. Still moving at c. Not c plus your running speed, just c. You get in a rocket ship. Accelerate to half the speed of light. Measure a beam of light coming toward you. Still c, not 1.5 times c, just c. This makes no sense. Velocity should add. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone on the platform sees that ball moving at 150 kilometers per hour. The speeds add. Simple, obvious, fundamental. Except with light, they don't add. Light always moves at c. Always. No exceptions. Ever. Scientists in the late 1800s knew about this problem. They built an experiment to measure it. 2 men named Michelson and Morley created an incredibly precise device. The logic was straightforward. Earth is moving around the sun at 107,000 kilometers per hour. If there's some invisible substance filling space that light travels through, we must be moving through it. So light should travel at different speeds depending on whether it's going with Earth's motion or against it, like swimming with a current versus swimming against it. They measured nothing, absolutely nothing, no difference whatsoever. Light moved at the same speed in every direction. They repeated the experiment, same result. Other scientists repeated it, same result. For 20 years, the best minds in physics tried to explain this. Every explanation failed. The measurements were too precise. The result was too clear. In vacuum, light moves at c regardless of how you're moving. Then in 1905, a 26-year-old patent clerk published a paper. His name was Albert Einstein. He didn't try to explain away the constant speed of light. He accepted it. He said this is a fundamental law of nature. Light moves at c in vacuum for all observers, period. And if that's true, if you take that seriously and follow the mathematics, something shocking emerges. Space and time can't be separate absolute things. They have to be connected. They have to be flexible. They have to change depending on motion. Here's how this works. Light moves at c, always, for everyone. But light also has to travel some distance to get from one place to another. Distance divided by speed equals time. If the speed is always the same, but observers disagree about distances, they must also disagree about time. There's no way around this. The math forces it. You're on a spaceship. In the middle of the ship, you turn on a light. The light spreads out in all directions. It hits the front wall and the back wall at the same time. You're in the ship, so to you, the distances are equal and the light arrives simultaneously. Simple. But someone watching your ship fly past sees something different. From their perspective, you and your ship are moving. The back wall is moving toward the point where you turned on the light. The front wall is moving away from it. So the light hits the back wall first, then the front wall. Same event. Two different observers. One says the light hits both walls at the same time. The other says it hits the back wall first. Who's right? They're both right. Simultaneity isn't absolute. Events that happen at the same time for you don't happen at the same time to someone moving relative to you. There is no universal now. There is no single moment that everyone in the universe agrees is happening right now. This isn't abstract philosophy. This is measurable physics. Build a clock out of light. Just a photon bouncing up and down between two mirrors. Each bounce is one tick. Put this clock on a moving train. From your perspective, on the ground, the photon doesn't just go straight up and down anymore. It travels diagonally, up and forward, down and forward. A zigzag path. That diagonal path is longer than the straight up and down path. The photon travels farther per tick, but the photon always moves at c. Same speed, longer distance, more time per tick. The moving clock runs slower. This is time dilation. It's not an illusion. It's not a quirk of clocks. Time itself passes more slowly for objects in motion. We've measured this with atomic clocks on airplanes. We see it with particles in accelerators. We account for it in GPS satellites. Every experiment confirms it. Every single one. And it's not just time. Space changes too. You're holding a meter stick. 1 meter long exactly. You measure it. Confirmed. 1 meter. Now you're on a train moving at very high speed. Someone on the platform watches you go by. How long do they measure your meter stick to be? Less than 1 meter. It's contracted in the direction of motion. Not because it's squished. Not because of any force. Because length itself is relative. Space is relative. Just like time. At everyday speeds, these effects are tiny, invisible, unmeasurable without atomic clocks. The difference between your head and your feet due to gravity is billionths of a second over a lifetime. The time dilation from driving your car is too small to matter, but the effects are real. They're always there. And at high speeds, close to the speed of light, they become enormous. A particle moving at 99.99% the speed of light experiences time 700 times slower than we do. From its perspective, it barely exists for an instant. From our perspective, it lives for a relatively long time. Both perspectives are equally valid. Both are true. Time is not universal. It's personal. It depends on your motion and your position in a gravitational field. Here's what this means. Every object in the universe has its own clock, its own rate of time. Your head ages slightly faster than your feet because it's slightly farther from Earth's center. Astronauts on the International Space Station age slightly slower than people on the ground. Not because of anything mystical, because time genuinely passes at different rates in different places. Why? Why does the universe work this way? We don't actually know. We can describe it. We can calculate it to incredible precision. Einstein's equations predict these effects perfectly. Every measurement matches the theory. But asking why the speed of light is constant, why space-time has this structure, why the laws are what they are, those questions don't have answers. These are the boundary conditions of our reality. They're given. They're facts about the universe that physics can describe but cannot explain. Einstein figured this out from pure logic. He didn't have particle accelerators. He didn't have atomic clocks. He just asked himself, what would have to be true if light really always moves at the same speed? And he discovered that it would mean space and time are woven together into a single fabric, space-time. And that fabric is flexible. It bends. It stretches. It changes based on motion and gravity. This is special relativity, the theory that explains how space and time behave. And it leads somewhere even stranger. If motion affects time, what about gravity? What is gravity actually doing? Einstein spent another 10 years thinking about this. And in 1915, he published General Relativity, the idea that gravity isn't a force pulling on things. It's the curvature of space-time itself. Mass bends space-time. Objects moving through bent space-time follow curved paths. We call that curvature gravity. Near a massive object like Earth, space-time is curved. Time runs slower, closer to the mass. This isn't because the mass is doing something to time. This is what gravity is. The bending of space-time. Black holes are places where space-time is curved so extremely that time nearly stops at the edge. Fall toward a black hole, and from an outside observer's perspective, you slow down, freeze, never quite cross the horizon. From your perspective, you fall through infinite time. Both are correct. Time is relative. Every GPS satellite, every particle accelerator, every measurement of starlight bending around the sun confirms this. General relativity is one of the most precisely tested theories in all of science. And it tells us that time and space are not the stage on which physics happens. They are part of the physics. They are dynamic. They change. They respond to matter and energy. This revolutionized our understanding of the universe. It explained the orbit of Mercury, which Newton's laws couldn't account for. It predicted that light would bend around massive objects, which was confirmed during a solar eclipse in 1919. It predicted gravitational waves, ripples in space-time itself, which we detected in 2015, exactly 100 years after Einstein published the theory. It predicted black holes, time dilation, the expansion of the universe. All confirmed. But even Einstein struggled with some implications of his own theories. He helped develop quantum mechanics, the physics of the very small, but he never fully accepted its core ideas. The notion that particles don't have definite properties until measured. That reality is fundamentally probabilistic, that the universe operates on chance rather than certainty. He famously said, God does not play dice, but every experiment suggests otherwise. Quantum mechanics works perfectly, completely. It's the foundation of modern technology. So here we are. We know that time is relative. We know that space is relative. We know that simultaneity depends on your frame of reference. We know that mass and energy are equivalent, connected by that famous equation, energy equals mass times the speed of light, squared. We know that gravity is curved space-time. We can calculate all of this with extraordinary precision. We can build technologies that depend on these effects being real, and they work. But we don't know why. We don't know why the speed of light is 300,000 kilometers per second and not some other value. We don't know why space-time has the structure it has. We don't know why the universe follows these particular mathematical rules instead of infinitely many other possible rules. These are the deep questions, the boundary questions, and they might not have answers. Or the answer might simply be, that's how it is. Science doesn't promise ultimate explanations. It promises accurate descriptions. It tells us how things work, not why they exist. It gives us predictive power, not philosophical closure. And that's actually okay. That's the honest approach. We describe what we can measure, we test what we can predict, we admit what we don't know, and we keep looking. The universe turned out to be stranger than anyone imagined. Common sense, intuition, everyday experience, all of it was a guide to a narrow range of conditions. At high speeds, in strong gravity, at tiny scales, the real rules reveal themselves. And those rules are bizarre. Time is flexible, space is flexible. Reality itself is not what it appears to be. Einstein saw this. He saw that intuition formed from walking around on Earth at low speeds cannot be trusted when talking about the fundamental structure of reality. You have to trust the mathematics. You have to trust the experiments. And you have to be willing to accept conclusions that feel impossible because they're true. A species that evolved to navigate forests and plains somehow developed the cognitive tools to understand the fabric of space-time itself. We built machines that confirm effects we can't directly perceive. We created equations that describe phenomena billions of light years away. There's something profound in that. The universe is comprehensible. Not fully, maybe never fully, but enough that we can decode its structure, predict its behavior, harness its laws. The speed of light being constant isn't just a fact about light, it's a window into the architecture of reality. Follow that thread and you discover that space and time are united. That motion changes time. That gravity is geometry. That the universe is far more mathematical, far more interconnected, far stranger than our ancestors could have dreamed. And we're still exploring this, still testing it, still finding new predictions, new effects, new confirmations. General relativity predicted things we only recently observed. Gravitational waves, black hole mergers, the shadow of a black hole, which we photographed in 2019. Every prediction holds up. Every test agrees with the theory. This is what science gives us, not comforting stories, not intuitive explanations, but accurate, testable, reliable descriptions of how reality actually works, grounded in evidence, refined by mathematics, confirmed by experiment. The universe doesn't owe us explanations that match our intuitions. It simply is what it is. Our job is to figure out what that is, to describe it precisely, to predict it accurately, and to be honest about the limits of our knowledge. Einstein did exactly that. He looked at a paradox, and instead of explaining it away, he took it seriously. He asked what it would mean if it were really true, and he discovered that it meant time and space are not what we thought they were. That took courage. It took brilliance, and it took a willingness to follow the evidence, even when it led somewhere impossible. The universe is not what we thought. It's weirder. It's more unified, it's more mathematical, and it's more beautiful than we imagined. After more than a century, we're still learning what Einstein revealed, still exploring the implications, still marveling at how a patent clerk armed only with thought and mathematics changed our understanding of existence itself. Time is not absolute. Space is not absolute. And that simple, strange, undeniable fact changes everything.